So we are going to start a course in quantum field theory. Okay? Before we are going to have a proper how we can study the course. So let me just have first 2-3 lectures, maybe part of introductory part of quantum field theory. तो इसमें हमारा आएगा what's the motivation of studying quantum field theory as a subject. And apart from also how historically the subject has evolved, है ना. किसी भी subject का evolution जो होता है it's not linear, zigzag होता है. Sometimes some result happens experimental, it's not explained, a new theory comes, sometimes theory gets rejected, so it passes through not in a linear, in a non-linear fashion. And there are various players which are involved as physicists or scientists who become their personal preferences, how they approach subject. It's not part of textbook, but it's always interesting if you want to study subject. अब ये है कि quantum field theory.
So there is a question: why do we study quantum field theory?
Yes, I'll just come to what you are trying to say. Quantum field theory. Quantum field theory एक हिसाब से it's epitome of achievement of physics. एक crystallized form है ना, achievement किसी भी चीज़ के at highest level. You can say quantum field theory can put it apart from general relativity. And then there are newer theories, frontier theories, which have some relationship with quantum field theory, like string theory. So we just come to see in that sense. So historically, so we say historically, it will be correct to say quantum field theory is part of our study. Of relativistic wave equations. Which includes or which is including इसमें Maxwell equation, Klein-Gordon equation, which you might have studied in your course in advanced quantum mechanics, and Dirac equations. So if you study books, तो normal इसमें जो proper way of studying this representation would be Wigner's definition of particles as representations of inhomogeneous Lorentz group. So this is a sophisticated way of we can normally, when we study starting quantum field theory books, we will say that particles can be represented in terms of inhomogeneous Lorentz group, which is basically a 10-parameter equation. So we'll see how particle representation can be seen in that way as part of some inhomogeneous Lorentz group. So I just before going to how we can properly represent in a formal way quantum field theory. So the point is what we are going to see is अगर आप वाइनबर्ग की फर्स्ट वॉल्यूम लिखोगे, if I just take the point of Weinberg का कोल या फरमान है, since he is one of the pioneers in the subject of quantum field theory, and he has written textbooks regarding the subject. So Weinberg says that, for example, if it turned out that some physical system is not described by QFT, it would be sensation, है ना? Sensation मतलब क्या होगी? News जैसी होगी, हाँ? Anything, any physical system is not described with quantum field theory. अगर कोई बात ये कहेगा तो it will be sort of sensation news. And if it turned out that the system did not obey quantum mechanics, it would be catalyticism. Catalyticism means किसी जगह आते हैं ना तूफान आता है या वो comes, volcano comes, या some disaster happens.
Natural disaster.
So you can say it as physicists, quantum mechanics should explain each and everything, physical part of the system. उसी की sophisticated form है quantum field theory as a formalism, which includes not only relativistic systems, particles having lower energies, but relativistic quantum mechanical systems, non-relativistic as well as in some formalism. Which is an important point which I'll explain. So the gravity of quantum field theory, these two statements, you can take it that way if you want to take it. Maybe although we can still say quantum field theory may not be the ultimate theory of the elementary particles, may not be ultimate theory of elementary particles. It can turn out that, for example, the more fundamental theory may be a string theory. It's besides the point that there can be relationship of quantum field theories and string theories. Some quantum field theories can be taken as string theories, or you can have a relationship of quantum field theory with string theories. That's besides the point. But you can say it because the whole process of scientific endeavor is continuous. So we know nature up to some scales, and we are pushing the boundary of those scales to next and next levels, to lower and lower dimensions and lower and higher energies. Got my point? Sorry. Initially we were knowing atoms, we are knowing matter in gross scale, then we had atoms, then we had electrons, then we had then we have molecules, then atoms, then electrons, then nucleons, so then we have quarks, and what are the sub-quarks? So these are different scales. But quantum field theory as such is the scale in which we normally describe things. Even in quantum field theory, sometimes we don't talk of, because there are various scales. For example, there is atomic scale, there is molecular scale, there is subatomic scale. Yeah, so we normally have different quantum field theories also, and there is a suitable paradigm उसको हम कहते हैं effective field theories. Effective. So on a given or effective field theory. So on a given scale, which quantum field theory may be relevant? There is a whole subject to it, which we are not going to say, but at least as an ideation, we can take it in that sense. अब quantum field theory जो normally है, what we are saying is basically quantum field theory is quantum mechanics. Quantum field theory is quantum mechanics plus relativity
Classical mechanics.
Which includes special theory of relativity. Because when the particles at normal low energies, quantum mechanics, but when we go higher energies, the particles have smaller mass dimensions. The effects of higher velocities they have some pronounced effects on the physical properties. So we have quantum mechanics plus relativity. But if we go, there is something called cluster decomposition principle. So I impended what we mean by cluster decomposition principle. So you can say there are ways how can quantum mechanics field theory can be basically how we can. So here I'll say, even though there's quantum mechanics, there's relativist quantum mechanics, but relativist quantum mechanics is not quantum field theory. Quantum mechanics or relativist quantum mechanics is embedded in quantum field theory. Quantum field theory is a sort of formalism or structure. Formalism means there are first principles, prior principles, which you can invent. They may have, what I should say, motivation some from mathematically some abstract principles, which are not derived a priori. But relativist quantum mechanics can be embedded in that first part of that formalism. So quantum mechanics can be taken as a formalism which describes the elementarity of the particles in that essence. Okay? In that sense. So even though if you go to ontology of quantum field theory, this is another debate. Ontology means when we talk of formalism, means whether that formalism is inspired by the essence, what we want to describe nature as such. Because as such, हमारे पास जो lab में जो data होता है, but as physicists, data is itself an information, but it's information without. We need to get meaning out of the data. We need to embed it into what it means. The data means to us. In its ultimate. Yes. But you need to interpret it from some first principles. And those first principles can be formulated in terms of some formal principles. So that's why that's the way we say quantum field theory as a formalism in that sense. अब ये है कि क्वांटम फील्ड थ्योरी में if we'll just draw a chart sort of thing. अब इसमें ये है कि ontology, maybe just like we have foundations of quantum mechanics, there can be foundations of quantum field theory also. Because जब हमने formalism को लाया ना, तो क्योंकि quantum field theory as a formalism, it should also satisfy the results of high energy physics, results of condensed matter physics, results of results of condensed matter physicists, results of what I should say, nuclear physicists, जो common results हैं ना, they should be explained by this quantum mechanical quantum field theory. And it should also have what's unknown. If explains nature up to this scale, we don't know. So there are some other theories, like string theories. You know? So it should also make some, if it's not in fundamental theory, you should have some, string theory should be, quantum field theory as string theory, part of some string theory formalism. So its scope is very large from QCD. So इसी को हम sometimes कहते हैं QED, QCD, है ना? Quantum chromodynamics, quantum electrodynamics. So these are, so basically there are a set of techniques also. A lot of techniques, observable techniques are there. How we calculate interactions and other things. And there is a whole formalism attached to it. So अगर मैं इसमें ऐसे बनाऊंगा classical mechanics, so there is a relationship between classical mechanics and
quantum mechanics.
So you can, so some in quantum mechanical textbooks you can always see that classical mechanics can be limited cases of quantum mechanics, and quantum mechanics may be a more fundamental field. This is the way we study in books, textbooks. the classical quantum mechanical analogues. It's a very interesting way how we can go from classical to quantum mechanics. The formalism of Poisson bracket, how we jump from classicality to quantum mechanics. And quantum mechanics, delta H tends to 0, we go to classical mechanics. You see that classical quantum correspondence. In the same way, there should be a correspondence of quantum mechanics and relativistic theory of quantum. So if quantum mechanics normally we see it's a low energy phenomenon, but relativistic quantum theory will include high energy thing also. So in limiting cases we should be arriving at quantum mechanics, and limiting cases we should be arriving at classical mechanics. So this is the chart we can have. And if you have general relativity, you have special relativity. So it's not only quantum mechanics, plus this special relativity and quantum mechanics, relativistic quantum mechanics. It will be like this. And from special relativity, okay.
So subject was?
No, but 11.
Ha?
Yeah.
Tu já badal conversamos hoje bate várias.
Just 10 to 11. So you can say tend to special relativity, relativist theory of quantum mechanics. So you can say classical mechanics, quantum mechanics, special relativity, and further when classical mechanics is you can get general relativity. And in modern days अब ये है कि if you have a यहाँ से फिर we can arrive at quantum field theory. Quantum field theory and general relativity together we get what? We get modern theories of quantum mechanical quantum field theories of general relativities. How we can unify quantum field theory with general relativity. So there have been attempts, so it will take us to the subject of quantum gravity in that sense. So subject of quantum gravity, so it's in itself. So but unless and until we know quantum field theory and apart from general relativity, we cannot, so that way also, even if you have to unify things at higher scales, quantum field theory should be embedded in that part of that theory. Now, अब ये क्वेश्चन हमारे पास ये है कि व्हाट is meant by elementary particle. So we say elementary particle ये है कि it's a particle whose fields appears in Lagrange. अब थोड़ा सा ये the definition becomes more subtle. So what do we mean that? For example, even if quantum theory describes things in that sense. How does field come into it? For example, when we have elementary particles, it's not a classical particle, it's point particle. But when quantum mechanical particle हम लेते हैं, it's not a particle in that particle sense. It has some spread. It's particle wave, particle somewhat embedded, and it's not entirely localized at one point. A question arises should we quantize it first, or should we quantize fields to get particles? There are two viewpoints, or there are two camps or two viewpoints. First viewpoint ये है कि because we are dealing with quantized systems or quantized particles, because once we go to relativistic quantum fields, quantum mechanics, so the things is already quantized. अब जो quantized है, ठीक है, वो quantized पहले से ही है, और we can see it's part of some property being generated by the fields in which it is immersive. अब हमारे पास दो व्यू पॉइंट्स. एक व्यू पॉइंट ये है कि which will endorse the idea of quantization and presumes necessity of finding a given classical reality or classical theory, then to establish a procedure to quantize it. तो हम कहेंगे पहले ही कोई क्लासिकल रियलिटी है, ठीक है, and we'll have some procedure. That procedure we are going to study later. What's canonical quantizing? So we'll take reality as classical, those particles as classical, and you will have some procedure which will quantize the system. ठीक है? This is one procedure. The other procedure is, और यह दूसरा कैंप जो हमारे पास है, it rejects this two-step reality. We'll take particles first as classical and then by some procedure we're quantizing it. वो कहते हैं कि नहीं, नेचर जो है फंडामेंटली क्वांटाइज्ड, ठीक है. सो वी कैन, और उनको हम कहते हैं क्वांटम रियलिस्ट्स भी. वो कहते हैं वी ट्राई टू फॉर्मुलेट क्वांटम थ्योरी without quantizing a classical system. अब ये क्या, what do you mean by? So वो कहेंगे nature is intrinsically quantum. Once we say we go from classical to quantum, ठीक है. अब अगर हम नेचर इंट्रिंसिकली क्वांटम है तो हम क्यों उसको फिर करेंगे वो प्रोसीजर, टू स्टेप प्रोसीजर करेंगे, पहले क्लासिकल ट्रीटमेंट देंगे फिर उसको क्वांटाइज्ड करेंगे. दिस इज वन वे. द अदर वे इज हम इंट्रिंसिकली नेचर को क्वांटम ही मानते हैं, ठीक है. सो विल फॉर्मुलेट आवर ह्यूमन क्वांटम फील्ड थ्योरी एंड क्वांटाइजिंग इट फ्रॉम द फर्स्ट प्रिंसिपल एब्सोल्यूट, ठीक है. And in a given setting, you can always go from suitable limits quantum to classical हम जा सकते हैं, जैसे quantum mechanics में जाते हैं. So under suitable limits, and even quantum field theory can go to quantum mechanical theory, can go to a classical theory. Yes. अब क्वेश्चन ये है कि जिस तरह अब there is a question which is there, जिस तरह हमारे पास classical quantum to classical है ना, counterpart. You can, from suitable limits, quantums can be reduced to classical things. अब ये what is the, if there is a theory which is intrinsically quantum field theoretical, उसका क्लासिकल काउंटर पार्ट क्या होगा, इसे क्वेश्चन मार्क, ठीक है। अब दिस इज दिस मच. So if I just summarize in that sense whatever we have said is that जो quantum field theory है ना, इसकी जो success है ना, it's very much successful. Quantum field theory is at the pinnacle of success. Pinnacle क्या होगी? हिंदी में कहेंगे चरम है ना, उर्दू में क्या कहेंगे? एट द ज़ेनिथ, उसको क्या कहेंगे? एट द पीक सक्सेस. किस हिसाब से? इट नॉट ओनली एक्सप्लेन्स क्वांटम मैकेनिक्स, QED की कुछ फिनोमेना, सो ऑल द बोथ लोअर एंड so whole range of things can be explained from, for example, and it has not only it has उसकी क्या कहते हैं, empirical success also. So you have experiments like Lamb shift, magnet movement, and other things. So it not only explains low energy physics, but it can explain high energy physics also. So जो experimental accuracy है, it's of the order of 10 to the minus 6 to the 10 to the minus 10 for elementary particles. For electronics, it's 10 to the minus 1 to the 10 to the minus 4. For weak interactions, it's 1 to 10 to the minus 2. And for strong interactions, it's tested to the distance of 10 to the minus 18 centimeters. 10 to the minus 18 centimeters कितना होगा? सेंटीमीटर की 0.000 कितना कम हो गया? इस स्केल पे भी we have been able to see this theory holds. So these are different scales. This is electrodynamic scale, molecular scale जो भी हमारे पास electron. So this is also QCD में भी है ना. So in the QCD का वो like we don't have QCD Lagrangian as such up to this date, but QCD के lot of properties can be explained by QFT. QFT में basically हम पढ़ते हैं QED and QCD. You go to any book of QFT, you have both QED and QCD. अब सिर्फ यहाँ पर 10 to the minus 18 सेंटीमीटर है, जो प्लैंक लेंथ है वो 10 to the minus 33 सेंटीमीटर है, जो 10 to the 18 का है ना 17 है ना, we don't know. अब इस स्केल पे when this operates at something called Planck length पे, when the gravity becomes important, इस स्केल पे, ठीक है? So we don't know. So there is a theory called string theory which has explained this thing. So if we have, once we will study quantum field theory, हम वहाँ एक running coupling constants करते हैं. We slide a given field theory on a given scale and extrapolate it backwards. At some point, we say where the universe started or where the unification happens. ठीक है? Up the point is कि quantum field theory should be explain us not only these scales but this scale also, ठीक है? And इसके नीचे it will be part of some other theory like string theory and so on and so forth. So the point here, if I want to summarize, so we can say quantum field theory हमारे पास एक formalism है to explain nature in its details, both bottom up या top down. Top down हो गया, you go from जैसे matter is ultimately it's made of molecules, then it's atoms, then it's made of protons, electrons, then it's quarks. फिर quarks के नीचे हमको नहीं पता है, हम कहते हैं strings के नीचे भी क्या है, or you can go from strings, quarks, then atoms, electrons, nucleons, molecules या solids या जो भी है, फिर matter की forms and so on and so forth. So you can have the quantum theory explains scales bottom up or top down. अब इन द मीन टाइम अब ये है कि एक हो गया क्वांटम फील्ड थ्योरी का फॉर फिजिज्म प्रोमिसेस एज दैट वे, बट जस्ट लाइक थ्योरी अपने आप में होती है कोई चीज़, बट वंस यू आर गोइंग टू अप्लाई इट टू सम कंक्रीट सेटिंग्स, तो हमारे पास कुछ रफ अप्रॉक्सीमेट प्रोसीजर्स होते हैं. तो उस सेंस में वो प्रिंसिपल्स वंस वी अप्लाई देम देयर कम वेरियस स्केल्स. उसी को हम, दैट्स व्हाई आई सेड समथिंग कॉल्ड इफेक्टिव फील्ड थ्योरीज. एक पैराडाइम है फिजिक्स में और क्वांटम फील्ड थ्योरी में, रेलेवेंट क्वांटम फील्ड थ्योरी एट ए गिवन स्केल. फॉर एग्जाम्पल क्वांटम फील्ड थ्योरी एज अप्लाइड टू कंडेंस्ड मैटर फिजिक्स. कंडेंस्ड मैटर फिजिक्स की स्केल अलग होती है, मैटर, मॉलिक्यूल्स, मिनी इलेक्ट्रॉन सिस्टम्स, क्वांटम मिनी बॉडी सिस्टम्स, है ना. इसी तरह क्वांटम फील्ड थ्योरी एज सीन बाय न्यूक्लियर फिजिसिस्ट्स, उनके लिए न्यूक्लियॉन्स होते हैं, टू न्यूट्रॉन्स, 2 प्रोटॉन्स, फिर उनका वो कॉम्बिनेशन, स्कैटरिंग आफ्टर एप्लीकेशन ऑफ श्रोडिंगर इक्वेशन के बाद we go to relative quantum mechanics. And even some quantum field theories in QCD, ठीक है. So how quantum field theories as applied in terms of effective field theories. So there is a procedure, इसको हम कहते हैं something called which you will study, और थोड़ा सा इसका आइडिया लेना चाहिए, renormalization और renormalizable quantum field theories. Just like आपके पास मैथमेटिकल फिजिक्स में आप पोल्स पढ़ते हैं ना, वहाँ सिंगुलरिटी आती है, तो उसको आप रिमूव करते हैं. तो होल क्वांटम फील्ड थ्योरी में भी एक प्रोसीजर है. While you are going to apply a given quantum field at a given scale, there come poles or they come unphysical things. How to remove those singularities in that sense? तो उसी में हमको there are procedures, those are known as regularization procedures. ठीक है. एंड उससे हमको renormalizable quantum field theories आती हैं. There are renormalizable quantum field theories and there are non-renormalizable quantum field theories. So for us, the interest will be renormalizable quantum field theories. And renormalizable quantum field theories may be they have some relation with the effective field theories. You got my point? They have some relation with the effective field theories. How field theories operate on a given scale. अब if I want to just इसी डिस्कशन को आप मॉडर्न डे फिजिक्स के साथ रिलेट करोगे, जैसे करंट थ्योरीज जो फिजिक्स की है वो स्ट्रिंग थ्योरीज हैं, ठीक है. तो वहाँ सब्जेक्ट बनता है स्ट्रिंग थ्योरीज एज क्वांटम फील्ड थ्योरीज. सो देयर आर सम स्ट्रिंग थ्योरीज व्हिच आर ड्यूअल टू क्वांटम फील्ड थ्योरीज. ठीक है. So if we don't take ultimately the nature की जो ultimate details हैं, they are not point particles, they are stringy, they are made up of strings. Strings का अपना एक topological structure होता है. तो strings, how are those quantum field theories dual to those string theories, or quantum field theories as subsets of string theories? This is a question also, because there is a whole zoo of जो इस तरह आपने पढ़ा था 1 particle states, 2 particle states, 3 particle, n particle states. तो string theories भी are infinite particle states. How those spectrum of string theories can be made, what I should say, dual to quantum field theories. तो Yang-Mills string theory जो तो इसमें normally so this is a whole new subject of research which will just as a information मैंने आपके लिए कहा. Even quantum field theory में one thing I missed is we also study Yang-Mills theories. Yang-Mills theory या gauge theory जो आप electrodynamics में पढ़ते हैं. How do we study the gauge theories are embedded in those? Once we said QFT is basically quantum mechanics plus Lorentz. Quantum mechanics plus Lorentz principle plus cluster decomposition principle, या तो एक तरीके से होगा, या अगर हम बिगिनर की एक फॉर्मुलेशन देते हैं, we study them as part of some inhomogeneous Lorentz group जो होता है, we study them as part of some representations of some inhomogeneous. These are two ways of representing. So the point which I want to mention is that क्वांटम मैकेनिक्स प्लस जब हम कहते हैं ना लोरेंस प्रिंसिपल हो, इट ओबेज स्पेशल थ्योरी रिलेटिविटी. तो उसमें आइडिया ऑफ गेज इनवेरियंस, हाउ डिफरेंट गेजेस आर इंट्रोड्यूस्ड. ठीक है, टू सी क्वांटम फील्ड थ्योरीज which part of our study. So this was a brief introduction of quantum field theory. And in the next class, maybe we'll try to see, before coming to the main subject, we'll see in 1-2 classes more how the birth of quantum field theories and various players which were attached to it. Players mean people who have discovered it, Schminger, Feynman, and that's whole. We'll see, have a bird's eye view how the subject developed. Okay? Anything you have to ask? Sure.
Revision's note. So, what we